Okay, so it's 2 o'clock, so welcome back everybody after lunch. We start the afternoon session and we are happy to have Shruti talking about on-shell recursion relations for 3 amplitudes. Please.
Can everyone hear me? Okay. So thanks to the organizers for putting together this great workshop. Week 1 was great. Week 2 is off to a very promising start. Hopefully it'll continue to be promising when I tell you about on-shell recursion relations for 3 amplitudes. So please stop me if there are any questions or if something is not clear when I write stuff on the board. Okay, so this is hopefully will take you to the point of the beginning of Melissa's lectures. So it should, by the end of this, you should be convinced that studying the Grassmannian is the same as studying tree-level amplitudes or cuts of loop-level amplitudes. And when I say cuts, you can refer to what Yara was talking about in the morning, where he told us exactly what we mean by a maximal cut or a leading singularity. Okay, so 3 amplitudes. So let's say AN3 is just a rational function. And it's a rational function of momenta and polarization. Right? And what makes these momenta and polarizations on shell data is the statement that summing over all of the momenta gives you 0. The momenta themselves square to 0, if you're talking about massless particles, which is what we'll do. And then finally, the polarizations of your particles are transverse. Okay? Good. So the first step to writing down any kind of recursion relation is doing an on-shell deformation. Okay? So I should say that recursion relation, really what I mean here is that I want to be able to build higher multiplicity and higher helicity numbers from lower multiplicity and lower helicity numbers. So to do that, I will need to introduce a parameter. I'm going to call this parameter Z. Z is complex. So then I can do the following deformation where I say that my new momentum 1, P1 hat, is P1 plus Z Q1. P2 is minus Z Q1. Actually, let's just call it Q. Okay. All right. So the reason that we can't start with just 1, and that's not the simplest thing, is because clearly you're not going to satisfy momentum conservation if you move 1 momentum off shell. And this should make you think more carefully about what you mean by a soft limit, because you can't actually stay on shell and take 1 momentum to 0, right? So hopefully this makes you think more carefully about what your mental picture of a soft limit is. But okay, so P1 hat square needs to be 0, but P1 hat square for us is P1 square, which is 0, 2 P1 dot Q Z plus Q square. Okay, so all of the coefficients of Z and Z square have to vanish, meaning that this needs to be 0, this needs to be 0. And in addition, if I look at this will imply that 2P2 dot Q also needs to be 0. Okay? So that's 3 conditions on Q. So up to rescaling, my Q is fixed. And my rescaling I can always absorb into Z. Okay, so what this means is that there is no more freedom in what happens to this condition. So whatever the condition is, it is. And if I write it down here, epsilon I dot P, so epsilon 1 dot P1 hat is epsilon 1 dot P1, which vanishes, plus Z epsilon 1 dot Q. Similarly for epsilon 2. Okay, but this should no longer be thought of as a condition on Q. It should be thought of as a condition on epsilon, right? So this is saying that this shift can only be an on-shell shift if my polarization vectors are chosen carefully so that whatever my shift momentum is, it's perpendicular to the polarizations 1 and 2. Okay. So yeah, so this is not just a function of the momenta, you also need to specify which amplitude you are shifting. Okay. All right, but this is an example of a on-shell deformation. It's also called the BCFW shift. So in terms of the spinor helicity variables that Yara introduced in the morning, 1 hat is then 1 plus Z2, and then 2 hat is 2 minus Z1. And you can check that these conditions are the same as all of the other conditions I wrote down. Okay. Good. So is this the only kind of shift that you can write down? So let's call this 1. This is the BCFW shift. But in principle, you could do other things. So there is also another case where you just shift 3, which is called a Risaga shift. But moving on, let's just think about all line shifts. Okay. So here what I'm going to do is every single momentum for every particle I'm going to shift in the following way. Okay. Now, clearly, there's additional information that I need here, which is that the sum over AI pi mu needs to be 0. Otherwise, this is not an on-shell shift, right? Okay. But there's something nice about this shift, which is you know exactly where in Z space your soft momentum lies. So if you want to take your ith particle soft, you know that just corresponds to the region of Z space where Z equals 1 over AI. Okay. Assuming that AI already satisfies this set of relations. And you can do a quick counting and see that this is n minus 5 free parameters. Okay. Okay. Let's look at a different kind of shift then. So you can also do something more exotic where you say, I'm going to take all of my momenta and shift it in the following way. Times Z, 1 minus Z, EI. Okay. So why this kind of shift is nice is because if you say Z equals 0, then I'm in 4 dimensions. Maybe I mixed it up. Yeah. This is 1 minus Z. This is Z. So when Z equals 0, you're in 4 dimensions. When Z equals 1, you're in 3 dimensions. Okay? So if in your recursion relation you have some information about your amplitude, some physical reason to believe that you know what is happening in 3 dimensions, but you don't know what's happening in 4 dimensions, you can use that inside your recursion relation to using a shift that's designed in this way. Again, you have to make sure that you can always choose pi mu 3D in a way that satisfies all of the on-shell conditions. But it is possible to do this. Okay, any questions so far? Yeah. Yes, yeah, implicitly. I mean, so here I'm not specifying what kind of function of P these AIs are, but here if you solve this equation, you're going to solve it in terms of PIs. I mean, okay, technically you can solve them in terms of the Mandelstam variables. So it's yeah. Okay. So one thing I just want to point out here is that your little group scaling becomes much more complicated because you're mixing up labels 1 and 2. Okay, just going forward. Okay, so how do you now use these shifts to write down a recursion relation? You say that you know that the physical amplitude is the amplitude evaluated at Z equals 0. And you know how to get something at Z equals 0. You do a contour integral around 0. And then you say that, yeah, you look at your shifted amplitude. Right? So a contour around 0 will pick up the residue at 0, which is exactly the physical amplitude. But in the Z plane, you know that there's other stuff going on. Okay. So this is where the physical amplitude is, but there are a bunch of other poles that are floating around your space. And unitarity tells you exactly where these poles are. They are when an intermediate propagator goes on shell. So I can now write this as a sum over, let's say, over Z naught, residue Z equals Z naught. So all I've done is I said there are some residues, and I can sum over them instead of summing over only the one at Z. Right? I just use Cauchy's theorem. But you can only use Cauchy's theorem, or rather, this doesn't contain infinity if Cauchy's theorem requires that an as z goes to infinity behaves at least as well as 1 over z squared. 1 over z. Yeah. So an of z has to look like 1 over z squared, an has to look like 1 over z. So showing that this is true is where the physics is. Right? So being able to show that whatever is in your integral vanishes correctly at infinity is where the physics lies. And so for BCFW in particular, let's say this is true for Young-Mills, for gravity, for dilaton gravity, and there are other examples. True for 5-4. Somewhat painful way of writing 5-4 because it's just the Feynman diagram expansion. But okay, so let me then write down the actual BCFW recursion relation. So there I know where the poles are, there's nothing at infinity. And so an equals sum over intermediate channels, residues equals zi. So the nice thing about the BCFW shift is that the way that it's designed, all of these are not quadratic, they are linear. So these are all simple poles. And in addition, each I corresponds to exactly one pole. Okay. But you can do other things, other relations. So this was for BCFW, which was our first shift. But if you look at the second shift, so the thing that this buys you, this shift, is that you might know what is the behavior of an at these soft points. Okay? So if I said that my amplitude behaves like an when p goes to 0 behaves like p to the sigma, then I can do something better. So I can write down a contour integral where it's an of z, and now I'm going to do this division by all of these ai to the z to the power sigma I, if you want different particles. Okay? The reason I can do this is because I'm not introducing any new poles when I do this. I'm just subtracting out zeros that I know already exist. Right? Okay. So then as long as this newly defined integral behaves well at infinity, which is going to behave better because I added this stuff in here, then this equals an of 0. And I can play the same trick. If at z equals infinity, it vanishes, then I can write this as a sum over residues, vi plus minus. So again, I've just factorized this, and but now it's a more complicated function that I have to evaluate the residue of. Okay. So here, this is precisely what BCFW doesn't have. So pi square of z is a quadratic function of z, and so you have 2 residues per factorization channel, whereas here you have exactly 1, because this is a linear function of z, because of how special the BCFW shift is. Should have said BCFW is Brito, Kirchhoff, Feng, and Witten, and I think the first time that this was considered was in 2016. by Chung, Kampf, Novotny, Shen, and Trnka, 2 of whom are right here. Yeah. Okay. And BCFW was 2005. Okay. Okay, so this allows you to then construct theories whose soft behavior is known. All right. Yeah. Finally, I'd just like to point out that even if you had shift 3, if you knew, for example, that your amplitude has to vanish in 3 dimensions, then you can draw something like this, which says an of z over z divided by 1 minus z. dz needs to be an of z. Okay. Okay, good. So, okay. So in this way, you can write down recursion relations. Yeah, and then all you're doing is summing over residues at simple poles. Okay. Are there any questions about how to write down a recursion relation for the various shifts that we wrote down?
Hello.
Yeah. Yeah.
So on the left hand side, there is no advantage using BCFW, right? If I am correct.
Sorry.
I mean, you anyway have to write A and Z.
Yes.
And
You mean in this relation? Yeah,
Yeah.
it's bought you nothing at this stage.
yeah.
Yeah.
So then what happened after that? I forgot.
So what happened after that is that I used the fact that unitarity tells you exactly where you have simple poles and exactly what happens on those simple poles, which is that the amplitude, sorry, maybe I went too fast, which is that the amplitude splits into AL and AR. There are some states here and there's some states here. Yeah, and so now these are lower point amplitudes. So I can now, so this relation over here, for example, tells you something at higher point solely from things that are lower point. Yeah. But it's good you asked because there's another thing I should have mentioned, which is, so this is PI, your intermediate momentum, and PI mu is some sum over some subset of momenta, right? All of the momenta here. So if it contains, let's say, P1 and P2, then BCFW actually, this equals P1 plus P2. So such a intermediate momenta won't shift at all. It's unshifted. So you require that 1 sits on one side and 2 sits on the other side. And this doesn't have to be color ordered. So I should say 1 and 2 can sit anywhere on opposite sides of the factorization channel. But yeah, in this sense, it's a recursion that you go from lower end to higher end.
All the poles in the next other relations point 2.
This one?
Yeah.
Yeah, so here it's similar, right? AL and AR are lower point amplitudes.
But you added some more poles there.
Yeah, but these are not poles. Crucially,
Okay.
I know that my amplitude behaves in this way. From physical principles, we'll get into like what examples exist of such things. But say a priori, you knew that all of your endpoint amplitudes had to behave in this way.
Okay.
That in the soft limit, they look like soft momentum to the power something. I mean this schematically, so maybe I should say this is like epsilon pi, and this is epsilon to the sigma I. But yeah, basically that means that all of these positions to this power are zeros of this amplitude.
Okay.
Yeah, because, and they vanish exactly with this degree. Yeah, so I can always subtract this out in this way. And I'm not generating any new poles. So I also want to point out, if you did generate new poles, this would not be the physical amplitude on this side. It would be a different object. Yeah. In fact, you can ask, for example, if you knew not that it vanished, but it gave some finite contribution, and you knew what that was, maybe you could add that to your recursion relation. And there are papers that do exactly this. Yeah. Okay. Other questions? Okay. So let's then look at what theories actually have this behavior. Okay. So with with BCFW, I already mentioned a few. So there's Yang-Mills, which is what we'll talk about mostly for the rest of this. But so the Yang-Mills is Lagrangian, right? Schematically, has a kinetic term. It has a term that looks like it's cubic with one derivative, and then it has something that is quartic with no derivatives. This is Yang-Mills Lagrangian. But the G that sits here, G Yang-Mills, is related to the G that sits here. And in addition, there's nothing that I can add here that is not higher derivative, right? So there is no ambiguity in terms of contact terms of what kind of amplitude I can write down at tree level. So let me just say what I mean. So I know that at tree level, I have some terms which are pole terms. Then I have some terms that are contact terms. So these are just terms that are local in pi.pj, epsilon i.pj, the invariants that have to make up my amplitude. These have a simple pole, and I know exactly what it needs to look like on the simple pole. So the fact that in Yang-Mills, there's nothing that I can write here is what is allowing me to do BCFW recursion. That's the physical principle that's allowing me to do BCFW recursion in the first place. So this is true, but more non-trivially for gravity as well. Okay, so then number 2 was the one where you know what the soft behavior is. Okay. So examples of this are anything that comes from spontaneous symmetry breaking. Almost anything, so it needs to be a symmetric coset. It has to be a symmetric coset. But if that's true, then you know that there is some positive sigma I for your particle, which is your Goldstone boson from that corresponding symmetry that's broken. So let me just say a bit more. G breaks to H, and then you get some Goldstone mode phi. For example, a pion for standard model, SU3 to SU2 breaking. And then this AN of phi, when the momentum related to phi goes to 0 is 0. And actually it's 0 with power 1. So sigma equals 1 for a pion. Which means that using these recursion relations, the nonlinear sigma model of such pions is constructible or recursible. Okay, so there are other examples like this, which if anyone is interested, you can ask now, or later. But these are some of the models, other examples, which is the Dirac-Born Infeld scalars, special Galilean theory, Akolov-Volkov fermions, etc. Okay. So this is like roughly how it goes, that there is some physical principle that tells you what kind of subtraction I can do. I put it into my recursion relation, and then I can, construct amplitudes of that theory. Yeah, so that was a bit quick. So are there any questions about that? You cannot use BCFW. Yeah, so one way of seeing why you can't use BCFW is precisely the argument for why you can use it for Yang-Mills, which is that you can write down contact terms that that would contribute. If you try to construct the amplitude like this, there are lots of contact terms at the correct derivative order that you can write down that would mix with your pole terms in principle. But I mean, you could do the non-fancy bootstrap, which is then to add all the contact terms and ask which combination vanishes in the soft limit, and you'd get exactly what the recursion relation would tell you should be the correct contact. Yeah. 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 Yeah, good question. I think F cubed. Okay, it's color kinematic dual, but that's not helpful. I think maybe it is. It is, okay, it is, yeah. I think it is BCFW recursable, but higher derivative than that is not. Yeah. So generic high derivative corrections to Yang-Mills are not BCFW recursable, but trace phi cubed. Sorry, trace F cubed is, yeah. No, in fact, it's the opposite, right? So you cannot add, so yeah, the more derivatives you add, the higher in mass dimension this amplitude is, the more momentum it has, so the more Z factors it has in the numerator. So generically, the higher derivative you are, the worse your Z behavior is, which is why in this special case of the soft limits, where you do have high derivatives, you can still do this recursion only because you knew that the amplitude vanished in some places. So you did the subtraction that made the behavior better. But you could, I mean, say you didn't do the subtraction, you just wouldn't be able to write down a recursion relation. Okay. Yeah, so maybe briefly before I erase, let me just say this was a sort of ignored thing in one of our papers from 2020. So I'd like to highlight it, which is just that if you look at Born-Infeld theory, which is some theory of vectors, abelian vectors, there is an argument that says that if I look at an amplitude with plus minus, like this, and the number of pluses doesn't equal to the number of minuses, okay? In such a case, the amplitude is known to vanish in 3 dimensions. So when I compactify to 3 dimensions, it's supposed to vanish. So in this case, for such amplitudes, you can show that the recursion relation that I wrote down over there has to hold. And once you know that it has to hold, you know that all I need to do is show that lower point helicity violating amplitudes vanish in order to show that higher point helicity violating amplitudes vanish. So basically what I'm trying to say is, in this theory, you can show that if n plus doesn't equal n minus, this amplitude is 0, and you can show it recursively because you know that in 3D, this thing vanishes. So this is like an example of how you can use recursion relations, even at tree level, to say something interesting to all n about the theory. So in this case, it would be the statement that Born-Infeld amplitudes do conserve helicity. They never violate helicity. Okay. Okay. So I'm going to just see if there are any questions about anything that is not BCFW, and then we can start talking solely about BCFW and in n equals 4 super Yang-Mills. Okay. So let's look at n equals 4 super Yang-Mills. So we discussed supersymmetry briefly, but I also remember on the first day, not everyone's hands went up when they asked, do you know what supersymmetry is? So I'm just going to quickly write down the superfield for n equals 4. And then it'll become clear that any super amplitude I write down is just a polynomial in these Grassmann variables. Okay. So here, my label A runs from 1 to 4, 4 being the n equals 4. And now I'm going to use this as my external state, meaning every time I write down an amplitude like this, actually what I'm scattering is not individual fields, like a particular positive helicity gluon, etc., but the full superfield. So whatever my amplitude is now a super amplitude, which is a polynomial in eta. And the different coefficients of this polynomial are then specific component amplitudes, right? So for example, coefficient of eta squared is what is called the maximum helicity violating amplitude. So the maximum helicity violating amplitude of n equals 4, which, for example, contains, I should say, contains an plus plus minus 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 plus plus plus. Okay, good. So this goes all the way until eta n minus. So actually, you'll notice that that's the only statement you need in order to run this recursion relation for Born and Feld to show that none of the amplitudes can violate helicity. But Young-Mills is different. You can violate helicity. You just can't. You can't violate it more than this. Okay. Okay, good. So in these variables, you now can write down the following on-shell condition. And now the game is the same. You want to write down an on-shell deformation that satisfies this. So you'd say eta IA hat equals eta IA plus z eta j a. So earlier we had chosen I and j to be 1 and 2, so I'm going to do that again. So when I do this with the BCFW shift, you get a super BCFW shift, which then will give you n equals 4 super Young-Mills, for example. N equals anything super Young-Mills. Okay? Okay. Yeah, okay, this is, yeah, okay, to the 8th. Is that, yeah. Yeah, okay, so actually let me write it like this. Okay. Yeah, and the small modification of your BCFW rule is then that an of 0, super amplitude, equals the sum over residues again. Except now I have to also consider all of the states that can sit in the factorization channel. And the way I do that is just by multiplying the super amplitudes together and then doing this Grassmann integral. So this just takes care of the fact that now it's not just a gluon that I'm exchanging, it's any of these states in my supermultiplicator. Okay. Okay, good. So now it should be clear that I can write down any tree-level amplitude in n equals 4 super Young-Mills just by gluing together 3-point amplitudes. Okay. So in particular, let's look at MHV. Okay, so okay. Can anyone tell me which one of these diagrams is actually the right contribution to MHV in BCFW? Or if it's both? Just, because it's after lunch. Okay, so they look both as if you need to, they look kind of like you need to include both. But, so, okay, maybe before that I should say that when I say k equals n k minus 2 MHV, and 1 is anti-MHV. Okay. So, right. So you might think naively like that both of these are good, that both of these are terms in your BCFW expansion. I'll also remind you that because supersymmetry starts at eta 2 to the n, you don't have 0, and you don't have n, or n minus 1 actually. Okay. And this has only 3 legs. So that's just how, these are just the vertices in Yang-Mills. Okay. So the reason is because of 3-point kinematics. So any 3-point amplitude, so rather any anti-MHV 3-point amplitude has the property that all of the angles are proportional to one another. Okay? So in this case, that means that 1 hat needs to be proportional to 2. Now, amazingly, I have just erased the BCFW shift, but this is actually just 1. So this is not a condition on Z. It's actually a condition on my external momenta. Right? So this is not true of generic momenta, and so this is not generically part of my BCFW recursion. This, on the other hand, you might say has the same problem, that this is a 3-point amplitude, but here n hat is proportional to n minus 1. Right? And n hat is not n. So this is not a condition on my external momenta, and so I do include this diagram, but I don't include this diagram. Right? So as long as I always make sure that I'm shifting 1 and n, I never have to consider 1 being attached to an anti-MHV vertex. Right? And this, so I should say that so far I've actually not, so I mean, the fact that there was only 1 diagram here is because I'm looking at color-ordered amplitudes, but the fact that 1 cannot be attached to an anti-MHV vertex is also true of gravity, for the same exact reason, because of 3-particle kinematics. Okay, good. So given that MHV is written like this, we can now write down NMHV. So NMHV. Yeah, so NMHV has a contribution that looks like 2 MHV amplitudes, I plus 1, I, summed over I. And it also has, as we saw before, one contribution of this kind, where you go from 1 to n minus 2, n minus 1, n hat. Right? So there's two types of contributions, but many, many more terms. So in the MHV case, there's only 1 term. Right? And you can see that this n depends on the n minus 1 MHV amplitude, which means that if I start drawing diagrams, such as if I told you, without telling you exactly why, that A4 MHV is this, then you know that the BCFW term for A5 MHV only contains 1 such diagram. So I'm going to call it an on-shell diagram. Yeah, and we'll go into exactly why this is the case in a second. But this is the amplitude. Okay. So while this looks like a loop, and we'll go into exactly why this is a tree-level amplitude in a second, but it makes sense that it's represented by 1 diagram. Yeah. Okay. Questions so far, and then we'll go into exactly what on-shell diagrams are. Yeah. Okay. So predictably, an on-shell diagram is a diagram in which all of the legs are on shell. Okay, so what this means is that if you look at this amplitude over here, it actually has no free parameters. So it's not like a loop integral that does have one free momentum. This actually has no free parameters. Yeah, so basically the way that you do BCFW is that you introduce a free parameter Z, and then when you put the terms together, you say Z equals Zi, right? So you take a residue. So the fact that, so basically you've introduced a free parameter, but it gets fixed. And that is precisely what this object over here does for you, which is called a BCFW bridge. So if you look at this and you think of this as, this is an anti-MHV vertex, this is an MHV amplitude. So these are just two 3-point amplitudes. This is something, some momentum, right? But this free parameter alpha gets fixed in terms of whatever momentum is flowing into that part of the subdiagram, right? And the fact that this gets fixed in terms of this is exactly the same as saying that Z equals Zi for this particular I, okay? So any MHV amplitude can then be written as this. This is anti-MHV. This is a big n-1 MHV blob. Actually, let me see. So this is 1, n-1, 2, n-2. So then this allows you to write down a bunch of Playbig graphs, but one for each MHV amplitude. And it should then also tell you how you can write down for NMHV, right? Because then I now have, yeah, so for NMHV, I can now write Playbig graphs which are like MHV, MHV with a bridge. Right? Plus the anti-MHV contribution. Okay, so these are what Melissa was considering. These are called Playbig graphs, planar bicolored graphs, or more commonly in physics literature called on-shell diagrams. Okay. So yeah, so this is a bit of a jump, but basically adding this allows you to do BCFW. And even if things look like loops, they are not loops, they are trees if each of the internal legs is fully fixed in terms of external data. So in this case, for example, this alpha is fully fixed by external data, and that external data is exactly the same as saying Z equals Zi. Right? So every time I attach a BCFW bridge, basically here, I would attach the bridge like this. Right? That will give me Playbig graphs like this. In the case of MHV, it's one on-shell diagram. In the case of NMHV, as you can see over here, it's multiple on-shell diagrams. In fact, multiple types of on-shell diagrams as well. Okay. Any questions? Okay, good. So now let's actually see what these black and white vertices mean. So far I've told you how you can break everything into black and white vertices. Now we'll see exactly what these black and white vertices are. Okay, so if you just write down what this is. 1 tilde, 1. Okay, so the idea of the Grassmannian formulation is very simple. It's the following. You take these two delta functions, and though they look quadratic or they look not linear in lambda, lambda tilde, you introduce an auxiliary matrix C that makes these delta functions linear in your variables, in your kinematic variables, lambda, lambda tilde. So the way that I'm going to do this is I'm going to integrate over this auxiliary matrix in the fall, and then I'm going to change these delta functions into these delta functions. C dot eta tilde, delta 1 cross 2, C dot lambda tilde. Okay, so I've rewritten this in terms of some integral over some matrix. This matrix, as before, fully fixed, right? Everything is tree level, so nothing, there's no free parameters, fully fixed by these delta functions over here. Okay, so if you look at this particular delta function, right, it's the same as this one, which means this tells you what C could possibly look like. So C is just, C has the following components: 2, 3, 3, 1, 1, 2, which then makes it obvious that C dot lambda tilde, this delta function is just the Schouten identity. So it's automatically satisfied with this C. And this over here is, so this over here is a matrix C perp that is perpendicular to C. Or maybe C dot C perp, depending on how the indices match up. So yeah, so then you can, so once you solve for C using these delta functions, you just take the minors of C, maximal minors of C. Maximal minors in this case is literally these three components, which is exactly these three brackets over here. Okay. So this should make it obvious that writing it like this, though right now has not gained us anything, is definitely equivalent. So these two lines are equivalent. Okay. Those two lines are equivalent. But and actually you can do this in general. You can introduce the C plane. And the C plane is so C plane is perpendicular to lambda tilde, which means if I draw all of my lambda tilde in a plane like this, then C is a plane that's perpendicular to lambda. Okay, my drawing is not so good, but I hope this makes sense. And then C perp is perpendicular to lambda. Another way of saying that is that lambda is inside C. Okay. Now we can do a quick dimension counting. So over here, I said that C is 1 times 3 dimensional, which means, and sorry, so lambda is 2 dimensional, which means that, sorry, lambda tilde is 2 dimensional. So for C perp, that has only 1 dimension, right? So, okay, let me just write. So dim C equals 1 is this case. Because lambda needs to sit inside C, you get restricted lambda. In other words, 3-point kinematics. So geometrically, this is how 3-point kinematics is realized. If you have dim C equals 2, then actually you can, and you need that C dot lambda tilde equals 0, right? So you can just say C equals lambda, because that's always going to be a solution. And there's only one solution at tree level. So once you can write down a solution, that is the solution. And then, yeah, for dim C greater than 3 or greater than equal to 3, then all you can say is that lambda sits inside C. Okay. Right. So, I mean, obviously, it's not only that you can write the black vertex, you can also write the white vertex. And so the white vertex is a similar integral, but now the volume of the C, the size of the C matrix is slightly different. But you still have the same delta functions. C dot eta tilde, that gives you the the supersymmetric delta function. Then you have the C dot lambda tilde. You have C perp dot lambda. And then you have a product of the minors. Okay. And it turns out that I don't even have to write this for this particular thing. I can write it for ANK for NK MHV. This will be replaced by K cross N, volume of K. This is 2K. This is 2N minus K. This is 4K. Okay. And this formula is now valid as an integral over cells of the Grassmannian. So this for now, let's say sum over diagrams. So this formula is now valid, and you can look at this book by Arkani-Hamed, Borgeli, Cacciazzo, Goncharov, Posnikov, Trnka from 2012. Where they discuss in detail all the different aspects of on-shell diagrams, how to get the Grassmannian cells, etc. But yeah, for now, I hope that this formula makes sense. All I have done is introduce this auxiliary matrix C. C is a matrix in the Grassmannian GRKN, which I have not said. I'll say that in a second. And then doing this integral exactly gives you the amplitude as written as a sum over BCFW terms. So C belongs to GRKN. Okay. Now, in particular, if you're doing adjacent BCFW shifts, it's greater than, it belongs to the positive Grassmannian, and also dim C is 2n minus 4 for any k. That's the cell that we're looking at. So I'll remind you that Melissa told us about how we should think about the Grassmannian. She said that we should think about this as cells. All of the cells are given by what the signs of the different minors of the matrix are, right? So you have these Plucker coordinates. You say that they are positive or negative, and that defines a cell of your Grassmannian. Right? So that's what Melissa told us about last week. So basically, this is why those kinds of things are important to us as physicists. It's because this sum gives you n equals 4 super Young ones. Yeah, so any questions? Because we'll move on. Okay, good. So I think the one hole in all of this is how do I connect the actual form of this matrix C to the graphs that I draw using these vertices, okay? But that also, Melissa told us. I will remind you though that in Melissa's lectures, she was in momentum twister space. And as you saw from the lecture in the morning, momentum twister space is a change of variables from spinor helicity, and here we're in spinor, or directly in kinematic space or spinor space. But okay, so let's look at the example we had over there, which is A5MHV. Okay? So this has one diagram, which is just a BCFW bridge, 5,1, sitting on an anti-MHV vertex, and then the 4-point amplitude. 2, 3. Now I can give these edges some variables like this, A3, A4, A5. And now I can construct the path matrix. Okay? So this might again be familiar to you from the lectures last week. So you say that your paths are going from 1 and 3 to 1, 2, 3, 4, 5. Right? And so 1 goes to 1 is 1, 1 goes to 3 doesn't happen. I've not drawn the arrows, but you have to believe me that you can always draw the arrows, and you can write down this path matrix, alpha 2, alpha 4, So once I do this, I can go back to this set of delta functions and say, what is the solution for these alpha parameters that satisfy these conditions, right? So once I have that set of alphas, I can now just find out the minors of that matrix, okay? And then you know what that's supposed to give. Famously, A5 MHV needs to give you the Park-Taylor factor 1, 2, 3, 4, 5. In other words, 1, 2, 2, 3, 3, 4, 4, 5, 5, 1 with the supersymmetric delta function in the numerator. Okay. So alternatively, instead of doing the path matrix, I could have also said that the only solution to this set of conditions for k equals 2 is that C equals lambda, and then minors of this matrix are just angle ij. And so then the product of minors in the denominator over here is simply the Park-Taylor factor. These are all alternative ways of doing the same thing. You're just running BCFW, but you're doing it via this auxiliary matrix C that lives in the Grassmannian Kn. Okay. Any questions? Okay. All right. So if you are familiar with Grassmannians, etc., then I would say that this is the point where you tune back in, because this will be slightly different from how we think about Grassmannians usually, which is instead of thinking of it as, so as Melissa told us, GRKN is k-planes in n-dimensional space. Right? So normally, how do you think of a k-plane in n-dimensional space? You think of k n-dimensional vectors. Right? In other words, you think of it as the row space of the matrix that you wrote down. Right? So you just write down k cross n, k n-dimensional vectors, which is k rows. Okay. But instead of that, you could think of it as the column space. So let's look at GR2n. This is a 2 cross n matrix. And then, yeah, so then you can write it like this. Yeah, this is 2 cross n, where each of these is now a point in P1. Right? So instead of viewing it as the row space, I'm now viewing it as the column space. And we know that these are projective. So all I'm saying is that I have a line, and that all of these alphas are just points on this line. Line meaning a line in P1. They live in P1. You can visualize this as being on a line. Right? So each of these is now the points over here. This is just a visual representation of the 2 cross n matrix. And now I can say that the positivity of a minor, so if I take this minor over here, the minor 1, 2 equals alpha 2 minus alpha 1, right? And so if I want to be in the positive Grassmannian, all of my minors have to be positive, meaning that this needs to be positive, or alpha 2 needs to be greater than alpha 1. And so then you see that, and given that this needs to be true, so any of the alphas, alpha I actually has to be greater than alpha 1, right? So that tells you that all of these must lie on one side of alpha 1. And you can do that again. So then you can say that alpha j needs to be greater than alpha 2 for all j greater than 2, right? And I can replace 2 by I, like this. And that tells you that these are just points on a line and they are ordered. Okay. So, and you know exactly what happens when I give you this matrix and put it into that formula. You know that it has to give you the Park-Taylor factor, right? This is just the MHV amplitude. So, yeah, so what that means is now I can say, now I can abuse notation a little bit and basically say that MHV n equals lines 1 through n. This is also a visual representation of the singularity structure of the MHV amplitude, which only involves holomorphic poles in consecutive labels, right? Because these are the only boundaries of this configuration happen when I have I and I plus 1, and then they coincide into one point. These are the only boundaries of this configuration, which is when I plus 1 is 0, which are the only poles of the Park-Taylor factor. So this picture accurately represents the MHV amplitude, or the Park-Taylor factor. Is that acceptable? Yeah. No, so all of these column vectors have to be points in P1. So it's a one-dimensional space. The only thing here that is non-generic is the fact that I chose to order this 1 through n. You could choose any ordering. It just wouldn't be positive. But in this one-dimensional space, it's a bit trivial because any ordering is positive according to some ordering. That is not true once I go up in dimension. So like in P2, if I gave you a configuration of points, and I said that every minor is positive, then it's not obvious that that means that, so basically what I'm saying is that if I gave you points on a line, there is some ordering, no matter what. It may not be the ordering 1 through n, but there's some ordering. But that no longer is true when I give you points in P2. Yeah, so there it becomes much more non-trivial that I have to be in the positive Grassmannian. Yeah. Yeah, yeah. It's a, yeah. Or rather, I would say it is a generic parametrization of GR2n positive. Positive GR2n, yeah. Okay, good. So now we can put things together, and now I can draw diagrams like the following. So to be clear, when I say this, actually I'm drawing the C matrix. But you know what happens when I give you the C matrix. You put it into that formula, you solve for the conditions, and then you calculate the form. So you get the amplitude. So if you do this over here, so as we saw, this is 2 MHV amplitudes, n hat, and then 1 NMHV amplitude. 1, 2, 3. Okay. Okay. Good. So now we would like to draw this type of diagram, which is a visual representation of the C matrix, except now you know that your C matrix is 3 cross n, which means it's n points in P2. Okay? So let's start with, let's start with 5. Minutes? Okay. Okay, so yeah, let's start with A5 NMHV. This has only this picture, right? Because there is no 4-point NMHV amplitude. So, right. So I know that this needs to be 1, 2, 3, 4. There's just this one diagram. Okay. But we know that this 1, 2, I is a line. 1, 2, I. Additionally, we know that I, 3, 4, 5 is a line. I, 3, 4, 5. And then finally, we know that this is not just the product of MHV amplitudes. You also have the 1 over pi square. Okay? And this you sort of have to believe me that when I do this, sorry. When I do this, I add this extra line. This is just the propagator. Okay. You can evaluate this, and it'll give you exactly the correct BCFW term. This is how you know that I'm not lying to you. Right? You actually do the calculation, it'll work out. So yeah, so this gives you one NMHV amplitude, but now you have the seed of your recursion. Because now when I have NMHV, I know what to do. I can draw now my configurations. Which are 1 hat, 2, 3, 4, 5, 6. 1 hat, 2, 3, 4, 5. 1 hat, 2, 3, 6. And these are precisely the 3 Rn variants that you get from the familiar BCFW expansion of the NMHV amplitude at 6 points. Okay. So drawing these Grassmannian configurations is the same as doing BCFW, but it's somewhat easier to visualize exactly what the singularity structure of each of the components is. And also, it makes it clear that this Rn variant is just the Park-Taylor factor Pt on 1 hat 2, 3, I1 times this Park-Taylor factor. So Park-Taylor I1, 4, 5, I2 times the last Park-Taylor factor Pt I2, 6, 1. Right? So all I did was read off from this picture that this has to happen. And these are the only ways in which I can draw these. So hopefully that gives you some idea of how to. No, I have much more than 10 minutes. Okay. Okay, fine. So, okay. So then we can make a few comments about this. The first comment is that C is supposed to be 3 cross n matrix, right? So actually that means that C has top dimension 3n minus 9. Okay. But I told you that all BCFW cells are supposed to have 2n minus 4 dimension. So this means that it is whatever BCFW cell I get out is codimension n minus 5. Okay. In other words, at 6 point, there's one condition on my minors. Right? There's one condition on my minors. And if you look at all of the pictures I drew, there's always one set of 3 points that are on a line. In short, there's always one minor that is 0. So in this case, it's 3, 4, 5, 1, 2, 3, 1, 5, 6. And that's precisely because you have to get the codimension of the cell right. So if instead I was to draw the C matrix of a generic configuration, that would be 1, 2, 3, 4, 5, 6. Just a fully generic set of points. Right? This is not a BCFW cell. To make it a BCFW cell, I have to choose one of the minors to set to 0 so that I reduce in dimension by 1. And as I was saying, so if I choose 1, 2, 3 equals 0, that will give me R1. 3, 4, 5 equals 0 gives me R3. 1, 5, 6 equals 0 gives me R5. I'm not going to tell you what R is, but it's basically the product of, you already know what it is because you can just read it off of this. Now, the other reasons why R is nice because it's a dual conformal invariant. And so building n equals 4 amplitudes out of these R invariants manifests dual conformal invariants. But for us, we can just consider it as just some product of Park-Taylor factors. Okay, good. So I hope it was clear, But actually, no, I take that back. I hope it was not clear what I did, because I did one thing which was a bit, I wasn't clear about how to do it, which is this diagram. So if you look here, I told you that adding a propagator is just adding 5 hat on a line between 5 and 1. But I never told you what it meant to have 5 and 6 on this line, right? And this diagram is the recursive diagram. So it comes from the fact that I started with the NMHV 5 point, 2, 3, 4, I. And then I multiplied the anti-MHV, so times MHV bar, I, 5, 6. And my claim is doing, so I over here, let's draw it. Let me know what we're talking about. Maybe I already drew it. Okay. 1, 6, 5, I, 1, 2, 3, 4. Okay, so then this I, because of 3-particle kinematics, is proportional to 5. So I can just replace this one by 5. And in addition, the anti-MHV is just the inverse soft factor. So if you were at Saurabh Pant's talk, one of the short talks last week, he was talking about how to do an inverse soft construction. So basically that relies on the fact that multiplying an anti-MHV factor like this is the same as just adding a point between 1 and 5. So now if I want to go another step further, this will be the NMHV amplitude, and I'll have to add 7 over here. Right? So that'll be the 7-point recursive step. So in this way, you can draw your diagrams. And now there is, yeah, all the cards are on the table. You know exactly how to do this. After doing this step, though, it is just a product of Park-Taylor factors. So, yeah. Good. So I just want to draw the n square MHV picture to show that it's not that scary. And then I'll end with a few remarks about all of these things. Okay, n square MHV. So n square MHV has this type of picture, this type of diagram. It has this type of diagram. And then it has the classic recursive part, which is this. Right? So you have 1 hat, n hat, n hat, n hat. Okay? So now I know exactly what to do, because in this case over here, this 3-point amplitude, so let's draw it. The 3-point amplitude is a triangle. We saw, sorry, not the 3, the k equals 3 amplitude is this triangle over here, which is NMHV, right? Those are the triangles we have been drawing over there. And it's connected here to an MHV amplitude. Draw the MHV amplitude. It's just a line. And in addition, so this ends with 1, there's a propagator. So I need to join this with the n here, right? And now it's, yeah, so that's it. So that is the configuration. I populate this with points. And you can see that it lies on a cube, which makes sense because all of this needs to be in P3, right? So that's the first term. I can do the same thing over here as well. So I can draw my first triangle. It has I over here. It has 1 over here. I can draw my MHV amplitude. And then again, I have a propagator. So this ends in n hat. And this is n. Now, once again, you have a recursive step, which is this. So you start at 6 point, where there is no n square MHV. You draw this, and then you can continue beyond that point, right? Okay, good. So this gives you, this hopefully gives you a sense of what you mean by on-shell diagrams, where the Grassmannian comes in, how to visualize the Grassmannian, and what a BCFW term, how all these things give you n equals 4 super Yang-Mills. Okay? I'm going to go ahead and say n equals 4 super Yang-Mills. Done at tree level. So I wanted to end with a few comments. So the first is that all of this is true, all of this is positive, all of this is nice and ordered, only when I did the following, which is given a BCFW term like this, the bridge I added, right, was always between two adjacent particles. But in principle, I could have added it between non-adjacent particles. There's nothing stopping me from doing that in the way that we set up our recursion. Right? And you can see immediately this gives you a non-planar diagram. So this is not a play-big graph. It's not a planar bicolored graph. It's a non-planar bicolored graph. And all I did was say that instead of doing 1 hat, n hat, I'm going to do 1 hat, I hat. Okay, j hat. Right? And then I add the BCFW bridge in that location, and it gives me a non-planar thing. So, and then once I have a non-planar diagram, and I try to write my path matrix, etc., C is no longer in the positive Grassmannian. Okay, so so remark number 1, planarity is, or positivity of the cell, both come from adjacent BCFW shifts. Okay, so non-adjacent will screw this up, but in a paper from 2022 with Yara, so this is Paranjape, Trnka, Zeng. We show exactly what comes out of doing a non-adjacent BCFW and how to think of these non-planar contributions. And I want to emphasize that the final amplitude is planar, always. Even in, already at MHV, you know that it just needs to be a line at the end. But there are various ways to write that line as a sum over non-planar things, and those non-planar things will precisely be the non-adjacent BCFW terms. I wanted to give one example, which is for MHV. Okay, maybe I won't. Maybe I'll just say my second remark, which is you can try to play a similar game in gravity. So in principle, all of the things I said over here are true for gravity. It's BCFW constructible. You can write down on-shell diagrams. It doesn't make sense to call them planar or non-planar because there's no ordering. So you can, it doesn't make sense to call them planar, non-planar. But you can draw the on-shell diagrams. You can write down a C matrix. You can do these things. But the form of the amplitude, or the form that I'm integrating C over, is no longer as simple. It's not some D-log form. It's some more complicated form. So gravity on-shell diagrams were studied in a paper by Arkani-Hamed and Jaroslav Trnka, maybe the first time, I think. But since then, there has been some work in the literature about these things. But overall, I would say that the niceness of the structures that are present in n equals 4 are definitely not present in n equals 8. And JJ will tell us about why one could expect that some of the niceness in n equals 4 should just double copy into n equals 8. But clearly not all of the niceness, because if you look at these on-shell diagrams, they are much less straightforward to calculate. Yeah. And they don't have as clear a interpretation as some, yeah, as these kinds of objects over here. Yeah, so that being said, you still can write down NMHV, let's say, for gravity, as some over contributions like this. Where these white blobs are MHV. And you have something over here that I don't want to define right now, but I do have in my notes if anyone wants to see. Okay, so there are such structures, and then these are sort of the analogs of R invariants. Now, of course, they're not invariant under anything, so calling them an invariant doesn't make sense, but they are the analogs of R invariants. Yeah, okay. So let me just end by putting up 3 questions, which I think are relatively open. One is the double copy. How does it play with this? So how do we see it? Here. Naturally, at the level of 3-point amplitudes, you can see it, but beyond that, not quite. Then there's the question of what other theories. So we spent a lot of time talking about n equals 4. I mentioned a bit about n equals 8. We also talked a little bit about the nonlinear sigma model. But what other theories can be recursed? And how? Of course, also a question. Yeah, and then finally, just all questions about gravity. So to do this, we assume that it had a 0 at a certain location that we know exists, but what other zeros exist of gravity? How many of these structures extend to gravity? Generally, gravity, question mark. Let me end there.
Okay, thank you. Thank you. Questions? Comments? Yes. We have...
The Nate. I mean, so you can do this. It's just that every time you do it, you have to, like you say, you have to keep track of exactly what is the Jacobian factor that you are. Yeah, yeah. Yeah, so I erased it, but the Grassmannian formula, you have to add something else into the thing so that it's not just a D-log form, it's some D-log form with a numerator or with a Jacobian, whatever you want to call it.
Yeah, the problem with gravity is that there is a mass dimension. Yeah. So it's no longer true that all these graphs have the same dimensionality. So therefore, you have to add some factors which bring.
You have to dress them in some way in order to make up the mass dimension. I don't know that construction, so I don't want to, yeah.
Yeah. This is just BCFW.
This is just BCFW.
Yeah. But you can rewrite it because even in BCFW for young males, for NMHV, you have these lower point NMHV amplitude in vertices. But you can rewrite them in terms of just MHV amplitudes. Therefore, it's because this is the analog of the R invariant. Yeah. You have to do a little bit of work, but the same thing works in gravity too. Okay. Yeah.
So you made a comment about inverse soft theorem. Can you just repeat what you said?
Yeah, all I said was just that if, yeah, here. So if you have a anti-MHV that you're going to multiply with this, right? Then the effect of that is just saying that whatever particular factor sat in this line needs to now have a 6 between 5 and 1. It's almost a kinematic fact. I mean, if you multiply the actual anti-MHV amplitude with this, you get.
Okay, so in the kinematic space, it's just shifting the momenta by the 6. Okay.
Yeah.
Thank you.
Shifting and then evaluating it at the appropriate residue. Yeah. So that is what, I mean, all of this in some sense is a way of making sure you're always evaluating at the correct residue.
Thank you.
Okay, more questions? Comments?
Speculative, but in the double copy beyond 3 point, do you expect while gluing you should have some kind of a kernel, KLT kernel that should feature, or?
I mean, we know that it's true. So you know that it's true that I mean, so the 4-point amplitude, for example, you know that 1, 2, 3, 4 squared US over T gives you this, right? Which is what you're referring to. So you might think that that happens at the level of on-shell diagrams, but
Yeah, exactly, yeah.
But I mean, yeah, it obviously happens at the level of the vertices, and then it happens at the level of the vertices here. And I know that it has to work out, but I don't know, like, at endpoint how that's going to look, because at endpoint it's not so simple as this, right? It's a sum over products.
Yeah,
of different orderings.
Yeah, but we know that it's like inverse of the biadjoint scalar, you know, the KLT matrix. So I mean, there was an amplitude interpretation of the kernel, at least in the CHY way when we looked at it. Right?
Yeah, I mean, this is true. I just don't know how it plays with the on-shell diagrams. I mean, maybe you can say more.
Okay, thank you.
If you take literally on-shell diagram with 3-point vertices, yeah, then the difference is just the Jacobian is just the KLT kernel or the trace phi cube. If you take the diagrams which have higher point vertices in the corners, then it's not obvious like how is it related, because you take products of 3-level amplitudes, there is no BCJ for the products of that form. Yeah, somehow it is there, but it's there like deeper down in more complicated way. But literally for the on-shell diagrams, the difference is just the trace phi cube.
Yeah. It might be nice for 4-point specifically because of this fact, but I think beyond that, again, you'll have to do.
Even beyond that, it's very speculative that we know that beyond that also it has the kernel is inverse of the biadjoint amplitude. Whether that inverse has a geometric meaning in terms of Grassmannian, I mean, it's very.
Yeah, but also as Shruti says, yeah, if the Young-Mills is a D-log form, like squaring the D-log forms and multiplying something is not a nice mathematical operation.
Okay, yeah. So we don't.
So it's kind of easy at the level of functions, but interpreting it as differential forms seems to screw up all the properties. Yeah. Okay, good. More questions? Yeah, I think it's time for the break. So thank you very much.
Thank you.
Shruti again.